Everybody, in this video we're going to be discussing some trigonometry, specifically solving right triangles, which is something we spend a lot of time doing in trigonometry. Right triangles are very, very convenient, especially when you're dealing with, of course, like the rectangular coordinate system, in which we can necessarily take any oblique line and make a right triangle out of it. But we use right triangles virtually everywhere. So I think it would be useful to know some of the terms and techniques behind solving them, starting with the fact that I am asking us to solve this right triangle. Notice I've already drawn a right triangle ABC here, and we've got two sides we don't know, and we've got one angle that we don't know. But the fact of the matter is this: when somebody asks us to solve a triangle, and it doesn't even have to be specifically a right triangle, it doesn't have to be, it can be any triangle. But the fact of the matter is this: solving a triangle essentially means finding out every single piece of information you can about it. So necessarily we could write, in this case, we say we want angle A, we want angle B, angle C. Of course, in this right triangle, we say angle C is 90 degrees, and angle B, we've already been given angle B. Angle B is 40 degrees, and of course, we want the side lengths as well. So we could say side AC, and we could actually write that like this. More conveniently, though, we could just say A, B, and C. Okay, and you notice I've arranged it kind of like this, and the reason why is because we associate the capital letter with the lowercase letter. They're typically arranged in a fashion such that they're opposite one another, but in this instance we know that C, side C, or the hypotenuse, typically the hypotenuse, okay, is 12. Now while I'm on that subject, it is the hypotenuse length, I want you to keep this in mind. This is a good thing, to just common sense if you're taking like a multiple choice test. But if this side is 12, we also know that A and B must necessarily be shorter than that side, since it is the hypotenuse, okay? Speaking of common sense, okay, let's go ahead and get started with solving this right triangle. The nice thing about solving specifically right triangles is that, of course, we know one angle is 90, but since it's a right triangle, if we're given any of the other two angles, because there are only three angles, but the other two, we know one thing about these other two angles. If all three angles add up to 180, okay, and 90 of those degrees are found at the right angle, then the other 90 degrees must be found at the other two angles. Of course, we've discussed this, and we say that the two acute angles in a right triangle must be complementary. That being said, we can already say then angle A, angle A must be 90, 90 minus, okay, angle B, but angle B is 40 degrees. So we can check to see, of course, if this works. 50 plus 40 is 90, and 90 plus 90 is 180, but here's what I'm trying to get across. When somebody says solve a right triangle and you know one of the acute angles, the nice thing about it is you could just use a simple difference to find the third angle here, okay? So we say this question mark now we know is 50 degrees, and that'll be handy. So at this point, the only things we don't know are side A and side B. And you might be saying to yourself, it would be really nice if we knew two sides of this right triangle, because then we could just use our Pythagorean theorem. Recall that that's just our A squared plus B squared, or the sum of the squares of the legs must be equal to the square of the hypotenuse. But in this case, we don't know either of the other two unknown sides. So we can't use Pythagoras here. We're going to have to rely upon our three trig functions: sine, okay, cosine, and tangent. So the question is, man, which one do I use and why do I use it? Well, I'll tell you what. It does not really matter which one you use. You could use any of these. And you might be saying, but then some of these, if I use it, I won't get the answer. For example, if we did the tangent of angle B, we could even write that. We say tangent of angle B, and that would be equal to opposite over adjacent, which would be A over B. And you'd say, well, man, that doesn't help us very much, even though I know that B is 40 degrees, because I don't know lowercase a and lowercase b. And you're right, but I want you to know this statement is still valid. And we often write statements like this if it's a tough nut to crack some of these problems, you have to take an indirect route. So I don't want you to, put that aside, but let's kind of take it back a little bit here. Essentially, we want to choose a trig function that is convenient in the sense that we can set up an equation or a relationship with some other values in which there's only one thing we don't know, okay? So what I'm getting at is this. Let's consider, how about this function 40 degrees? Because it's convenient. We could say 50 degrees, but 40 degrees, I'm looking at angle B. But we happen to know angle B. Now let's say we're in search for angle A here, okay? We know angle B, we don't know A. What we'd like to do is set up a relationship between this angle B and the side length A and another side we actually know. We want only one thing we don't know, which would be A. So the question is, which trig function from angle B here, which of these three trig functions would we choose to relate A to 12, okay? And we say SOHCAHTOA, or we could look at another definition of the trig functions, but we say in this case we want this maybe over this, but opposite over hypotenuse. Okay, so opposite over hypotenuse, that's our sine trig function. Let's go ahead and set this up and just write this down and see what it kind of looks like here. So we have sine of angle B, which was 40 degrees in measurement, is equal to A over 12. Okay, A over 12. So now we've got this really nice trig equation in which there's only one thing we don't know. And of course we can get a number for sine of 40. Unfortunately, it's not a 0, 30, 45, 60, or 90 degree angle in here, which we would know. But we say, okay, so in this case, we'll use a calculator for sine of 40 degrees. That'll be really easy to do. But we need to get A by itself. So the question here needs to be, so how could we necessarily get A by itself here? Well, you'll notice A is being divided by 12. What we'll do is we'll just multiply both sides by 12. And I'm actually going to put the 12 in front over here. That's common. It's very appropriate. But we say 12 times this number, sine of 40 degrees, that ratio, is equal to A. Okay, so the nice thing is, if you were to write this on a test, say, there's no way the teacher could look at you and say, no, that's absolutely wrong. As a matter of fact, this wouldn't be a bad idea to leave it like this. This is an exact value. Notice I use an equal sign here, okay? But, often we're doing metrics, okay? We're measuring things, so we want to change this to a decimal. So what I'm going to do is I'm going to pull out the calculator, and we're going to evaluate this sine of 40 degrees, okay? So already, this is a good habit I have, I think. And actually, I can't write that. This time it's going to be an approximation. I'm going to write approximately equal to A. But I'm going to leave this blank, and we're going to go evaluate sine of 40 degrees. So we'll just pull out the calculator here. I'll clear these things out. So sine of 40 degrees. No, I don't want to buy the calculator now. Okay, so type in sine of what? We say 40 degrees in parenthesis equals. Now you'll notice we've got a huge decimal here. And so I think it's about time we had a conversation about we'll have the sig figs or significant digits conversation another time, but it is entirely appropriate in trigonometry to typically go out to 3 decimal places. Anything past that, you're going to be really accurate. And hey, good for you. I am a fellow nerd, so go for it. But for the sake of, I know my class, I ask my students to go out to 3 decimal places. So we say 0.6427. Since we're observing the 2 as being in the thousandth spot here, and it's the 7 next to it, we'll call this approximately 0.643. Okay, so 0.643, we'll put that back. Come back over here with 0.643. Now notice everything to the right of this, it used to be a 2, this 3 here is gone. So this is only an approximation. And that's the reason why I'm using this. Okay, you could also write at the end of this. I know people think I'm trying to be funny when I write this, but you could write 0.643-ish. Okay, because that's all it is. But for the sake of this argument, that's all we really need to know. So now we need to find 12 times 0.643, and we should have whatever A-ish is. So we say we'll take that last number times 0.643. And you'll notice here when I pull the dashboard back out, we could take 12 times this number here. As a matter of fact, we'll write times 12. Well, we'll wait here a second. But you notice this answer right here is really accurate. But since we've accepted the fact that we're going to go out to 3 spots here, okay, in this case 3 sig figs, but we say we're going to actually take the 0.643. 0.643 times 12, okay? We do that just for the sake of consistency. And you notice you get a 3 decimal number back, but 7.716, okay? We say A is approximately 7.716 units in length. We'll do that. Oh, that's what I'm looking for. We'll do this in both colors here. But now that I've got this, the best thing to do I've found is to kind of come back up to your triangle and scribble that in. 7.716, okay? 716. And then we're going to write that in over here. That was side length A. It's approximately 7.716 units in length. And of course that was less than 12. But yeah, so that would be the protocol for finding, say, a side of a triangle when necessarily you only knew some angles and only one side, okay? At this point, though, what we said we were doing is solving the triangle, which means we need to find all lengths and angles on it, and so we need to find angle B now. So The nice thing about this is it's a right triangle and we now know two sides. So we could get away with using the Pythagorean theorem, and I promise you that's what I want to do. But let's say I didn't want to do that, okay? Let's say I now wanted to solve for b using a trig relationship, okay? So now going back over to this triangle, we know A, we know, say, this is equal to C here. But we could maybe take this top angle here, this 50 degrees, and do the same thing we did with the 40 degrees, but we could say, you know, sine of 50 degrees, which is the top angle. Remember, sine is opposite over hypotenuse, but I'm doing this because we don't know b. We could put that in up here. And we do know the hypotenuse, 12. This would be the same situation we worked out last time, okay? And you would necessarily go through the same steps, but we'd be solving for b. However, simpler would be to use Pythagoras here. So something squared, leg squared, equal to hypotenuse squared. So let's go ahead and fill in some values. The hypotenuse is 12. We said A would kind of go here, but we say A is about approximately 7.716. So by all rights, we should be writing, these are only approximately equal. But we say B goes here. Okay, that's a B. So we say, all right, 7.716 squared. Let's kind of come back over here. We say 7.716, which I already have up here. I'm going to take that to the power of 2. And it says we get approximately 59.53. This was going to go to a 7. So 59.537, 59.537, just to make this clear, ish, plus b squared is now equal to 144. Okay. So now what we got left to do is, of course, we're going to subtract this value from both sides. So we say b squared would be equal to 144 minus that 59.537-ish. And so we say b squared is approximately equal to, let's take this, we'll do this calculation here. So 59.537, well, I'll go minus 144, we'll just call it positive, but a positive 84.463, so 84.463. So now, taking the square root of both sides, we say b equals, or is approximately equal to, the square root of 84.463, which again, I would not be able to look at you and say, no, you're wrong, but we do want a decimal, so let's go ahead and write the square root of 84, so we say root 84.463 in quantity, and we'll take a look at what we have here. We say, okay, so 9.190, and we are actually going to write that 0, 9.190, okay, ish. So we say now we've got b. Let's come back up here and write it on our triangle and our data matrix here. But let's switch back over to green. Approximately equal to 9.190. We write this 0 here just to tell our audience that, hey, we actually did round to that spot. Now, the last thing you might want to look at is this. Now that I've got all my links, are they reasonable? Okay, now recall that, of course, the longest side is the longest side because it is opposite the largest angle. And this reasoning kind of goes counterclockwise. We say that the shortest side length would necessarily be opposite the smallest angle. So since B, okay, angle B was the smallest angle, we see the side opposite was 7.716, which is less than 9.190, but not by a lot, okay? And the reason why, side B was bigger in the first place is because angle A, okay, ooh, I've got my letters mixed up here. This should be A and this should be B. But regardless, we say angle A was slightly larger, so the side length A across from it is going to be slightly larger than side length B. So it's a good set of techniques and suggestions in this video. We're going to take it a little bit further in the next